Hello. Is it Palms? And I guess Chinese girl as well. 'Cause I'm seeing some Chinese characters in the name, so I don't know if it's quite the Chinese or just people being creative with the Chinese. Okay, welcome one and all. I hope you guys are well. I'm actually picking up from where I left off with the grade 11s and trigonometry. Trigonometry. That's the one. That's the place. That's our destination. Hope your study has been good, that it's been better than it's been better than anything that you've ever seen. So today, guys, yesterday I went through the basic sort of like layout of trigonometry. We looked at what the definition of trigonometry is, the fact that we are dealing with triangles, the measurement specifically of triangles, sides and angles. And we focus particularly on right angle triangles, but that does not mean right angle triangles are our only focus, right? But in this particular instance, grade 10 and 11, right angle triangles, and therefore we looked at the definitions that pertain to trigonometric basic trig ratios, sine, cos, and tan. We then looked at why it is that we look at the acute angle whenever we are dealing with a basic trig ratio, and why it is that we have to reduce a particular angle to acute, because in a right angle triangles, with the exception of the 90-degree angle, all the other angles are acute. So therefore we need to obviously reduce to an acute angle. We then looked at special angles, 0, 30, 45, 60, 90, 135, 225, 180, 270, 315, and 360. We looked at how now we can actually utilize our calculator whenever we want to find the actual ratios. We don't need those triangles. We can actually use our calculator. Then I sort of like showed you guys how you can use the mother graph of the sine, cos, and tan graph to basically read out the special ratios, for 0, 90, 180, 270, and 360 specifically. But then for 30, 45, 60, obviously we can utilize our calculator. And then I spoke about how 135, 225, and 315 have to be reduced using our function values, 180 minus, 180 plus, and 360 minus. Then we looked at the unit circle, quadrants. We looked at why it is that in different quadrants certain trig ratios are positive, why others are negative. We looked at function values, and as we were looking at function values, looking at 180 minus, 180 plus, and 360 minus, we then turned our attention, and it was in that moment when we were turning our attention to co-function values, which is where I'm going to pick up. So we looked at function values, and I basically told you yesterday that, in order to determine the sign for each trig ratio when you are reducing a function value, you can simply utilize your calculator, and that is you can substitute in the place of theta like 1. And when you do that, your calculator will give you the sign of the trig ratio. So without even using the quadrants, you can just basically determine the sign of each trig ratio in each quadrant by using or substituting in the place of the angle theta just 1. You can substitute 2 if you want, 3, 4, just as long as this angle is an acute one. And then you can basically determine the sign. 180 minus is positive, whereas 180 plus is a negative sine theta. That's for function values. We have 3 function values, 180 minus, 180 plus, and 360 minus. And all of this assist us to be able to reduce all angles that are greater than 90 or less than 0. They help us to reduce them to acute angles. which we refer to our reference angles. So now we're going to look at cofunction values, and cofunction values are special in that with cofunction values, sine theta changes to cos, okay, and cos changes to sine. By cofunction values, I mean 90 minus, 90 plus, 270 minus, and 270 plus. Guys, these are what we refer to as our co-ratios or cofunction values. They basically lead to a change in sine to cos or cos to sine. They are the only function values that lead to a change in trig ratio. Okay, that is still looking at within one unit circle, meaning from 0 to what? To 360. Whenever you have 90 minus, 90 plus, 270 minus, or 270 plus, expect this change. Sine to cos, cos to sine. So for example, let's say you have sine of 90 plus theta, and I say to you, reduce sine 90 plus theta. So first question you ask yourself, 90 plus theta, in which quadrant is 90 plus theta? So if we look at the Cartesian plane, 90 plus is in this quadrant, 270 minus is in this quadrant, 270 plus is in this quadrant, and 90 minus is in this quadrant. So these are what we refer to as reduction of a co-ratio. Okay, and honestly speaking, guys, our first preference whenever we reduce, we try and use function values as much as possible. Okay, because function values do not lead to a change in trig ratio. So when we reduce, we try and look at these as our primary, we sort of like they are our first strategy point. We check if 180 minus, 180 plus, 360 minus, because we know there's no change in trig ratio, just a change in sign. With co-ratios, there's definitely going to be a change in sine, and also sometimes there's definitely going to be a change in trig ratio from sine to cos, cos to sine. But then at some instances also, there's a change in what? In the sine as well. So for instance, 90 plus theta is in which quadrant? It's in the second quadrant, right? So in that second quadrant, do you still remember who is positive? Remember, it's sine that's positive. So that means we are going to get a positive answer. But then since it's 90 plus, that means that there's going to be a change in trig ratio. It was sine that we were given, so the trig ratio is going to change to cos. Okay, and then obviously 90 plus falls away, and then the acute angle is the angle that we reduce to. So sine here has changed to cos. Why? Because we are dealing with cofunction values. And this is the only time sine changes to cos or cos changes to sine, is if we are having these 90 minus, 90 plus, 270 minus, or 270 plus. Let's look at another one, cos of 90 minus theta. 90 minus theta, which quadrant? 90 minus theta is in the first quadrant. Okay, 90 minus is in the first quadrant. Do you still remember who is positive in the first quadrant? In the first quadrant, we know that all of the trig ratios are positive. So that means we are going to get something that is positive. But then, of course, cos is going to change to sine. And then 90 minus falls away. We have theta as the acute angle that we basically then write next to the trigonometric ratio. Okay. Let's look at another one. Let's say cos of 90 plus theta. Once again, 90 plus theta is in which quadrant? It is in the second quadrant. How is cos in this quadrant? Cos in this quadrant is negative. But then, since we know we are dealing with co-ratios, that means it changes to its co-ratio sine, okay, and then it becomes negative sine of theta. Okay, so please, guys, take note that with cofunction values or co-ratios, there's a change in trigonometric ratio. Sine changes to cos, cos changes to sine. And that is the thing we just need to remember, or ought to remember. Okay, let me just do one more. Let's say sine of 270 plus theta. Now, the thing is, it's only in the new Mind Action series textbook that they officially sort of like recognize 270 plus and 270 minus as a co-ratio in our South African CAPS syllabus. So as such, in this new mind action series, we can then obviously take this as a co-function value. So what we do is we're going to ask ourselves 270 plus, in which quadrant is 270 plus? So 270 plus is in the fourth quadrant. And in the fourth quadrant, do we still remember who's positive? Yes, it's cos who's positive. But the trig ratio we've been given is sine. So how is sine in that fourth quadrant? It is negative. But because we are dealing with a co-function value, sine changes to what? To cos. And then, of course, we then write down our acute angle, which is theta. Okay. Guys, that's basically how we go about with our co-function values. There's always bound to be a change in the trigonometric ratio. I'm just going to do one last one just for us to basically just kind of wrap it up. I'm sure you guys get the drill now, and you guys are sort of like sorted, and you're like, oh, okay, so sir, what you are saying to me is that 90 minus 90 plus 270 minus and 270 plus leads to a change in the trigonometric ratio. Yes, that's exactly right, dearest so-and-so. And do you mean, sir, as well that the sign changes in accordance to the given trigonometric ratio? Yes, you are exceptionally right. That's spot on. So sine 270 minus theta, once again, sine 270 minus theta is in which quadrant? It is in the third quadrant. In the third quadrant, how is sine? Is sine positive or negative? Sine in this quadrant is definitely what? Negative. So we then write negative. Then sine changes to the trig ratio, cos. Then 270 minus falls away. We write down the trigonometric, the acute angle, theta. Okay. So guys, I hope you guys are now sort of like full on convinced about these co-function values. And surely from now onwards, you will never fall short from actually doing what is right when it comes to these co-function values. The next thing I want to look at, guys, is negative angles. Negative angles. What do I mean by negative angles? This means these are angles that are less than 0. Angles less than 0 degrees. Okay. So if we look at standard, let's say we had sine of theta minus 180 degrees. Sine of theta minus 180 degrees. Now, when you look at this, first and foremost, you're like, okay, theta is first and the angle is second. But instead of this angle being positive, the angle is negative. Okay. That is what we mean by, so the angle here is actually negative. Okay. So what we basically can just do for negative angles is simple, guys. All we do is we just add 360 degrees. Think about it. If this angle is negative, it means we are no longer operating within the unit circle 0 to 360. We have basically left the unit circle 0 to 360, and we have entered the realm of negative angles. So what we want to do is we want to restore our working within one unit circle. So in order to accomplish that, what we do is we add a full revolution, or in other words, we add a full complete 360 degrees until we can actually enter the 0 to 360 interval, or I would say the 0 to 360 unit circle, if you want to put it that way. So we add 360 until, okay, and we add 360 however many times until we can fully completely say we are now within the full 0 to 360 unit circle again, where we have positive angles and it's between 0 and 360, full stop. So let's look at this, guys. So with sine theta minus 180, what we are going to do, we are going to first add 360 because we have a negative angle. This will help us to slowly but surely approach this 0 to 360 interval. So that's what we are going to do. So we take our calculator and then we just say negative 180. We take the negative angle exclusively and we just say negative 180 plus 360. What? Not 390. What am I doing? Sis, what is this? Sunday. And I'm doing such nonsense. Negative 180 plus 360, you get 180. And this 180 is positive. 180 is also within the 0 to 360 interval. So I love this. Now this minus 180 is now 180 degrees. Why? Because I just added 360 degrees to negative 180 to get 180 degrees, which is an angle within the 0 to 360 interval. So I am now safe. I am safe and I am ready to basically write this in the correct order. Theta plus 180 is the same thing as 180 plus theta because addition is commutative. In other words, it doesn't matter the order in which I place the 180 and the theta, because theta plus 180 means the same thing as 180 plus theta. Okay. Now you can see this is a regular normal function value. Let us evaluate it. 180 plus theta is in the third quadrant. How is sine in the third quadrant? Sine is negative, so therefore the answer is negative sine theta. Okay. Or always remember what you could do to determine the sine, make life very easy. You could say sine 180, my 180, right? It was 180 plus, right? It was 180 plus. Then you just put 1 in the place of theta. Look at the sign. The sign is negative, guys. So that means I'm going to have a negative answer, but I'm going to write negative sine, obviously, of the acute angle. Okay? And that is how I evaluate that answer. Okay, negative angle, is it difficult, guys? Surely it must not be. Let's do one more, or maybe we can do two more. Let's look at tan theta minus 540 degrees. Oopsie, look at this one. Is the angle positive or is it negative? So once again we have theta minus 540 degrees. This 540 degrees is very negative. I hate negative things. Yeah, well, you must change this negative energy to positive energy. So what we do is we add 360 the first time. Let's check if we add 360 the first time. Does that lead us to the 0 to 360 interval? So negative 540, we add 360, we get negative 180. These guys are still negative. So still using the calculator, we add another 360. We push it again. We add 360 the second time. There we go. We have positive 180. That's what we were looking for. So then we can write tan. Now we know that addition is commutative, so let's not even write it in the wrong order. Let's write it in the right order. First time. So our minus 540, after adding 360 twice, we eventually got to 180 degrees. And this is what we need to do. We need to add 360 however many times until we enter into the 0 to 360 interval. And that's what we want. We are now there, 180 plus theta. Now we can evaluate the what? The trig ratio, because we are in familiar ground. We can reduce the function value. So so now we're going to ask ourselves, 180 plus theta is in which quadrant? Third quadrant. How is tan? Tan is positive. So then the answer is positive tan of theta. Okay. Remember, guys, I'm still always saying that, if you guys feel like, you are bound to make an error, guys, there's a mark with making sure that the sign of the trig ratio is correct. You making sure that this is 100% correct, is a full mark, and even with simplification, it's a full mark. So we cannot butcher this thing, getting the the trig ratio correct, please, guys. So that's why I insist on this thing, that if you see that push comes to shove and you are so lazy, you shouldn't be though, please utilize. You can see it's positive, this thing, so the sign is positive. Okay, yeah, all right. Blessing, I'm guessing you're probably a first timer. I reckon you're probably a first timer, because that's why you are saying this thing is hard. You're only showing us the easy part. Of course, Blessing, the only way you will receive your blessing in life is if you get the basics done. Once you get the basics done and they are easy, then the complex stuff is not complex. It's just the easy stuff stacked together. So you need to first sort out the easy, sweat the small stuff, then you will see the difference in the difficult stuff. Trig is very easy, but you need to be 100% spot on with the easy stuff. Okay, so Presh, let's take your example. Let's say, for instance, it was cos of x minus 360. Love it, I love it, I love it. So this one, all you do is you are going to, like you said, we are going to add 360. Chua pagati inside. What does that give us? 0. And that's beautiful, because all that means is that we now have cos of x. Okay, yeah, we now have what? Cos of x. Yeah, so that means that is our answer. That is beautifully our answer. And if you are maybe thinking, hi, it can't be said, then maybe what you can do for yourself is you can just write cos, and then you can put inside that bracket, in the place of x, you can substitute that 1 minus the 360, if you know what I mean. Then you can see for yourself, look at the sign. It's positive. The outcome is positive. So the fact that when you add a 360, you still get cos of x and it's positive, that is basically your answer. And that would basically apply for every trig ratio. Because where we are here, we are at the first quadrant. And at the first quadrant, all trig ratios are positive. Okay. Okay. So I hope that clarifies that one. All right. Let's see, let's do just one last one, then I will definitely change things to something else. Yeah, still we are at negative angles, so what do? We add 360 until we fall into the 360 interval. So I'm sure you are grabbing your calculator just as I am. You are saying 1080, you are adding the 360 the first time. You're like minus 70, when you add the 360 again, you minus 360, you add the 360 again, you get 0. So that means this is cos of theta. All right. Okay, so guys, thank you. I hope you guys get the whole negative angle thing. Then let's turn our attention away from negative angles and look at angles greater than 360. Angles greater than 360 degrees. Okay, angles greater than 360. So with angles greater than 360, all right, obviously with them, let's say for example we had cos of 450 plus theta. So you can see 450 plus theta, 450 is an angle that is greater than 360. This is not within the 0 to 360 interval. So since the angle is greater than 360, what would we do this time round? Instead of adding 360, we are going to subtract 360 degrees. However many times, until what? Until we enter the 0 to 360 interval. So this is basically what we are doing with angles greater than 360. Okay, we subtract 360 until. So I'm going to grab my calculator again. When I say 450, I'm going to minus 360, and then I get 90. Okay, I get 90 when I subtract 360. Am I now in the 0 to 360 interval? Yes, I am. So I'm going to then say cos of 90 plus theta. Okay, then I'm going to evaluate this. This is a co-function value, so that's very important. This is a co-function value, so therefore what do I say? Remember, with co-function values, I remember the rule for co-function values. It means cos will change to sine eventually. But first, let's evaluate. 90 plus is in which quadrant? It is in the second quadrant. How is cos there? Cos is negative. But then we write the co-ratio and we write down the acute angle. So the answer is negative sine of theta. Okay, so for angles greater than 360, guys, all we are doing is we are subtracting 360. That's all we are doing. We are subtracting 360 until we enter into the zone of 0 to 360. Let's do another one. Sine of 810 degrees minus theta. Minus theta. I'm glad, Amo. Those are the kind of comments that I really love. I'm glad that you're understanding now. And I guess if someone else was coming on here and seeing me explain these basics and they're like, that is too easy and stuff, I hope you guys appreciate the fact that there are people that are probably not in the same level of understanding. It's maybe you are. So appreciate the fact that I'm explaining the basics to them. I guess that's being part of a community. I hope people who come onto the platform and start following me and seem to have maybe a little bit of impatience because they feel like I'm explaining something and it's too basic for them, have the patience to actually allow me to do that for the benefit of those that do not maybe yet understand so well. So 810 minus theta degrees. So what do we do again? I said for angles greater than 360, we subtract 360 multiple times until we enter into that 0 to 360 interval. So 810, gonna grab it, 810. Let's subtract 360 the first time and see where do we land. 450. We need to subtract again, another 360. 90. Woo! So we have sine 90 minus theta. Whoa, we are in familiar ground. Now that we are in familiar ground, we can definitely reduce this thing. Okay? Yes, thank you, Pigel. I really appreciate that validation. So true. So true. Okay? I really appreciate that validation. Because it's easy, Trigo, if you understand the basics. So that's why I'm explaining the basics. Thank you so much, Pigel. I really appreciate underscoring that exactly. So 90 minus theta is in which quadrant? It's in the first quadrant. How is sine there? Sine is positive. But then since it's a co-ratio, we are very sensitive that, hey, this is co-ratio. It's co-function stuff. So sine becomes cos, and that's very important. And then we write down the acute angle. Okay. Guys, that's what we will be consistently doing with angles greater than 360. We'll constantly be adding 360 until we enter into the 0 to 360 interval. And then after doing that, we write the new function value or the co-function value. We reduce it and then bam, easy capeasy. All right. And once again, I want to remind you that if you want to be able to get what the sine of the actual trig ratio is, please, guys, okay, Tapelo says, can you repeat that sin theta? Okay, so sine 90 minus theta. 90 minus is a co-ratio. It's not a function value. It's not just a function value, but it's a co-function value. So since it's a co-function value, we know with 90 minus, 90 plus, 270 plus, and 270 minus, the trig ratio sine will change to cos. If it was cos, it would change to sine when we reduce it. Okay, so that's something that is special and unique about our co-function values. And I repeat, your co-function values are 90 minus, 90 plus, 270 minus, and 270 plus. The trig ratio sine changes to cos, and the trig ratio cos changes to sine when we are dealing with the co-function values. Different, of course, from when we are dealing with the function values, 180 plus, 180 minus, and 360 minus, because the trig ratio doesn't change. Okay, so that's something you need to be aware of. Those are the basics that you need to be aware of, because if you are not aware of those basics, then you will basically not be able to do a lot of things correct, especially when you are dealing with simplification of more complex problems. Otherwise, sine 90 minus theta, like I said, 90 minus theta is in the first quadrant. That's what we ask. Where is 90 minus theta? 90 minus theta is in the first quadrant. How is sine in that quadrant? Sine in the first quadrant is positive because all trig ratios are positive in the first quadrant. So therefore you write positive, then you change the sine ratio to cos, and then you write down the acute angle because 90 minus falls away, and that's the answer. Okay, so guys, that is negative angles and positive or angles greater than 360. Hopefully you guys have been able to really appreciate those and appreciate them well. Something else I want to look at very quickly whilst we are still at this, because prachtig, it is a co-ratio. It's a co-ratio. That is a rule in trigonometry, that whenever you have a co-ratio, co-function 90 plus, 90 minus, 270 minus, and 270 plus, all of these guys, all right, 90 plus, 90 minus, 270 minus, and 270 plus lead to a change of trigonometric ratio. Cos changes to sine if it is sine, and sine changes to cos, and cos changes to sine whenever we reduce these trig ratios, these trig co-ratios or co-function values. So when we reduce these co-function values, sine changes to cos, cos changes to sine. It's a standard rule. But with 180 plus, 180 minus, and 360 minus, there is no change in the trigonometric ratio. That's very important. There is no change in the trigonometric ratio with 180 plus, 180 minus, and 360 minus. Okay, thank you so much, Pigela, for the heart. We really appreciate it. So let's look at these ones, okay? Kind of like your square ratios, or sometimes you could say exponential in nature, all right? So let's look at the sine squared of 180 plus theta. So first and foremost, what I need all of us to understand is when we have a exponent, we need to first take the exponent out and then write the trig function value that was given inside the entire thing, all right? So what this squared means is that it is squaring just the trigonometric ratio. It is not squaring the coefficient of the trigonometric ratio. So let's say if there was a value here, the value would basically be placed outside of the square. Very important. So then what do? You evaluate what's inside. 180 plus theta is in which quadrant? It is in the third quadrant. How is sine? Sine is negative. Then you basically say negative sine of theta. Now, when you apply the square back into the trigonometric ratio, you get a positive sine of sine squared theta. And the reason why we get a positive sine squared theta is because a even exponent applied to a negative sign changes the negative sign to positive, because this is like saying negative times a negative, and a negative times a negative, guys, we know is equal to a positive. In actual fact, if you multiply a negative sign even number of times, you will always get a positive answer. So what we conclude then is any squared function value will always result in a positive answer. Any squared function value will lead to a positive answer, and that is something that is very important to note. Let's look at this one. So number 2, sine squared negative 720 plus theta. Okay, so obviously here you can see this is a what? It's a negative angle. So what we do first and foremost, before we do anything that has to do with anything, maybe what we can do is we can take out the square, write the sine negative 720 plus theta, because we know obviously that everything will be squared. And then let's look at the negative angle. We add 360, because this is a negative angle. We go ahead, we add 360 multiple number of times until what? Until we fall into the 0 and 360 interval. Okay, so there we go. We get 0. So that means sine of theta. Because when we add 360 the second time, we get 0 plus 360. So basically we have sine of theta. Okay. And then if we apply the squared, we get sine squared of theta. Okay. Yeah, guys, so that's basically how we are moving. We are rolling. So whenever we have the square, please just take note that the square needs to be taken out. You evaluate the function value. You apply the square back. You should get a positive answer. Whatever will be the result of the reduction of the function value will always eventually, after the square has been applied, will lead to a positive answer. Okay. And that's kind of like something that we always need to be mindful of. Okay. Look at this, tan squared 180 minus theta. Just want to look at that one as well, just very quickly. So tan squared of 180 minus theta. So first and foremost, we take out the square. We write the function value nicely inside the square bracket. Then we evaluate tan. 180 minus theta is in which quadrant? Obviously, it is in the second quadrant. How is tan? Tan is negative. All right. But then, of course, when we apply the square to the negative, we get a what? A positive tan squared theta. Because the even exponent obviously leads the negative sign to be positive. Okay. All right. Let's look at one other one. Half of sine squared 180 plus theta. So once again, we have a square. So what we do is we square the trig ratio. Please, guys, take note here. Take note of what I've just done. I did not take the half and put it inside and square it, because this square applies to the trig ratio alone, not the coefficient half. It is excluded. Okay, yes, it will be lovely, it will be. This half is excluded. So please, guys, I want you to note this, that the coefficient of the trig ratio is not included as part of what we need to square. We square only the trig ratio and its function value, which is very important. We evaluate the trig ratio whilst the half is out there in the cold, waiting, pleading to come inside, but not allowed any admission, because only the square will be applied to the trig ratio. So evaluate 180 plus theta. 180 plus theta is in the third quadrant. How is sine in that quadrant? It is negative. So we have negative sine of theta. Then of course we apply the square after evaluating the trig ratio. The answer that we get is what? Half, obviously. Yeah, Tori, so pleading to come back, but never being allowed admission until the square is applied. Now the half can be multiplied to the sine squared theta, so we have half sine squared theta, and that's our answer. Okay, it's just that sometimes people tend to think that this coefficient is also going to be affected by the square, and that's where people mostly go wrong, because they apply the square even to the half. But let's note that the coefficient is unaffected. Left in the cold, it stays in the cold. Okay, so the coefficient guys, is very important. The coefficient is unaffected. Okay, that's very important. Okay, that's what you thought also, Valentine or Valentine. My goodness, we just left the month of February and there's someone who has to be called Valentine's. Are you kidding me? Hi, Soga. Okay, I don't understand what this question is. So you don't reduce 180 in double angle as it is greater than 90 degrees. Yes, Tori, so it's always the case with the coefficient. Oh, that's your name. Icon. What a name. What a name. What did they say to you during Valentine's? Your friends and your family and all those that love you. Did they say Happy Valentine's, Valentine? Are you kidding me? Yeah, that's quite a turn of events. That's quite interesting. Okay, and then guys, let's move on to just one last thing, which is a very essential and necessary tool. I feel like I've covered the tools, but now I need to just do one last tool, and that has to do with what we refer to as identities. Identities. Hello. This is me. I am identities, even with people most, we all have a sense of identity. Who are you? When I ask that question, who are you? Who am I? Where do I come from? Where am I going? That type of thing. Identity is a big thing, eh? Who you are, very important in the world that we live in to really know who we are. Not just like from a social construct sort of like perspective, but from a perspective of real depth as to like, who are you? So identities, we have two identities that we basically have in trigonometry. We have what we refer to as the quotient identity. Now, the word quotient means what, guys? Do you know? Someone tell me what the word quotient means. I will love it. Quotient. Yes, Luba is lumbering. Yes, quotient means divide. So therefore you understand when I say tan theta is equal to sine theta over cos theta. You see? And the proof is in the pudding, guys. The proof is in the pudding. Say for instance we had a right angle triangle in the Cartesian plane. Okay, this is x, this is y, this is r, this is theta, our acute angle. All right, so what is sine theta according to our right angle triangle that is in this Cartesian plane? And I mean, this is the definition for sine, right? Sine theta is equal to, I want to see it in the comment section. Sine theta is equal to what? Tell me now, please. I know, an exceptional singer, like it's not even funny. No, it's grade 11, guys, grade 11. Please don't lie to the masses. We're busy with grade 11. But of course, the grade 12s will benefit as well, because as they go ahead and do what they do, the grade 11 knowledge is important as a foundation. So sine theta, according to this triangle, opposite over hypotenuse. In other words, y over r. Thank you, Luba. Then what about cos theta? Cos theta, according to the triangle, adjacent over hypotenuse means it is x over r. Okay? Now, let us take the right hand side. I just want to prove this identity very quickly, guys. Okay? So sine theta over cos theta. Sine theta over cos theta. Sine theta is x over r, right? Cos theta, no, I'm just kidding, guys. Sine theta is not x over r. Cos theta is, sine theta is y over r. Cos theta is x over r. So this is like saying y over r, meaning sine theta, divided by cos theta, which is x over r. Let's rewrite this. Y over r divided by x over r. Does that look a little bit better? Because there seems to be too many lines here. Y over r divided by x over r. So I rewrite it. Y over r divided by x over r. in grade 7, I think, you guys learnt y over r times r over, yes, y over r times r over x. Yes, very good. Then the r and the r, what do? R divided by r, what happens there? They cancel. You are left with y over x. The question is, guys, what is y over x according to our triangle? Y over x is opposite side over adjacent. What is that? That is tan, isn't it? That is tan theta, right? That is definitely tan theta. Okay, so that then validates why we say the quotient identity tan theta is truly equal to sine theta over cos theta. No doubt about it. We use a right angle triangle in the first quadrant where x is our adjacent side, y is our opposite side, and r is our hypotenuse. We prove that indeed the division between sine theta and cos theta is literally y over x, which is tan theta. So it makes sense why we say tan theta is equal to sine theta over cos theta. It has grounds. This thing is true. It is true. It is the truth. I need someone to say hallelujah, because it's Sunday, guys, and when truth is spoken, people need to affirm with huge, amazing hallelujahs. Anyways, let's move on from there. Then number 2, let's look at the second identity, the trig identity. We look at it. It's called the square identity. Okay. Amen. Hey, Tumelo and Sban, you can see. Yeah. Square identity. And the Masungulu. Square identity. The square identity is this one. Sine squared theta plus cos squared theta is equal to 1. In the same vein, there is a proof for this thing. Remember, guys, the proof is just simply something that makes us understand that these statements, these identities are true. Like they are not some fabrication of some figment of someone's imagination. They are legit. So sine squared theta plus cos squared theta is equal to 1. So let's take this same diagram of ours. We can obviously use in terms of y, x, and r. What is sine again? Because we're going to take the right-hand side, the left-hand side, which is, in this case, sine squared theta. Sine squared theta plus cos squared theta. This time round, what is sine in terms of y, x, and r? Sine is opposite over hypotenuse, so it's y over r. But then what do? We square it, right? What about cos theta? Cos theta is x over r. Then what do? We square it as well, ne? Now, after doing that amazing job of squaring it, laws of exponents, they say when we have a division of different bases and there's a exponent raised, we can actually apply the exponent to the numerator and the denominator, as long as the relationship is one of division between two bases. So let's apply the exponent at the top, y squared. Apply the exponent at the bottom, r squared. Do the same thing with x squared. Do the same thing with r squared. Then we have two fractions. What does the law of fractions say? When we have two denominators and they are the same, that allows us to do what? To add the what? The numerators. So I'm sure you can see this is y squared plus x squared. Yeah? But if you remember, this here, x squared plus y squared, it reminds me of a theorem that we refer to as Pythagoras. Pythagoras seems to say that r squared is equal to x squared plus y squared. That means in the place of x squared plus y squared, we can substitute r squared. This is y squared plus x squared. This is the same thing as saying x squared plus y squared, because addition is commutative. Okay, guys, it's not my network that is bad. Dite, My network is flowing like the river. At least it's saying good connection. So I don't know if it's maybe someone else's connection, yours maybe, but mine is flowing like the river. Unless someone else can confirm that the connection is not flowing like a river, then maybe a confirmation can come from the masses that be. Alright, so then y squared plus x squared, that's the x squared plus y squared, that is r squared, guys. That is r squared. Because Pythagoras, we can replace x squared plus y squared with r squared. This is r squared at the numerator because of Pythagoras. What is r squared divided by r squared? It is 1, wasn't it? It is 1. But isn't that what we said about sine squared theta plus cos squared theta, the fact that it's 1? It is, so it's true. We've proven it. We've proven it, guys. We proved that indeed sine squared theta plus cos squared theta is 1. Now, guys, that gives us full reign to use these identities. Okay, all right. So just one more time for the person who didn't get me there. Y squared over x squared, as the squares apply to the numerator and denominator. X squared over r squared, as the exponent is applied to the numerator and the denominator. When the denominators are the same, fractions, in the laws that be where fractions are concerned, we cannot add two fractions until we have the same denominator. In this case, we have the same denominator, it's r squared. So then there we have it. We have r squared in the denominator. Okay, then what is y squared plus x squared? Y squared plus x squared, that is equal to r squared. Why? Remember Pythagoras? Pythagoras says the square of the hypotenuse side is equal to the sum of the square of the other two sides. In other words, when we apply Pythagoras, the square of the hypotenuse being the r, is equal to the sum of the square of the other two sides, x squared plus y squared. So there we have it, r squared is equal to x squared plus y squared. So that's why in the place of y squared plus x squared, which is the same thing as x squared plus y squared, I substitute the r squared in its place. And then r squared divided by r squared, when we divide something by itself, it gives us 1. So indeed, sine squared theta plus cos squared theta is equal to 1 as per the proof. Therefore, that's why this identity is true. It holds that sine squared theta plus cos squared theta is equal to 1. Now for Dieter, who was basically not here for the tan proof, I was saying for the tan proof, the quotient identity, it says tan theta is equal to sine theta over cos theta. Vincent, that is kind. I'm not a genius more than the fact that I've learned Vincent, you could be literally in my position now. If you spent so much time with the maths and you've been teaching it for ages, and it literally becomes second nature, it becomes a part of you. So certain things are just in your mind and heart because you know them so well. So I want to say, even my learners that are here, you can become so familiar with the concepts and the content as you spend more time with it, so much so that you can become so good that you can articulate it to other learners and you can be able to assist them and help them, thus assisting yourself the more you assist others, you see. So don't be scared to go and share this with your friends and tell them, from what you learned, so that they can see and they can even say to you, you are a genius. Okay. So let's go back to this one. Tan theta is equal to sine theta over cos theta. How? So I took the left hand side, I took sine theta, I wrote it in terms of y and r. Okay. I'll do that, Presh. I took sine theta, wrote it in terms of y and r. Sine theta is equal to opposite over hypotenuse, so it's y over r. Cos is equal to adjacent over hypotenuse, it's x over r. Then what I did is I took sine theta over cos theta, which is my left hand side. and then all I did, sine theta is equal to y over r, cos theta is equal to x over r. So this means y over r divided by x over r, in other words. Then I took this division, change it to multiply. You know what happens to the second fraction whenever you change divide to multiply? This x over r becomes r over x. It's the inverse. Okay, since we change divide to multiply, which is the inverse operation, then the second fraction, you know, it like does the same thing. X over r becomes r over x. Then these two cancel. I'm left with y over x. But we know that y over x, if we go back to the diagram, opposite over adjacent. Y over x is literally opposite over adjacent, which means it's tan theta. Okay. Dearest Presh, you said I must go back to negative angles. What I had said about negative angles, Presh, was that whenever we have a function value and we can see that the angle, yes, non Cindy, so before practicing you must first understand the concept. Once you understand the concept, then you apply the concept consistently, because you know, if you have knowledge that you've gained, the only way you can drill that knowledge in your mind and heart is if you do problems that basically hammer in that particular concept that you've learned. That's how you ensure that the knowledge stays in you for longer. But if you don't practice, then you are basically making the knowledge to stay lesser. And you know, so if you want to have knowledge for a long time, you must practice and you must do it consistently. Theta minus 180, negative angle, right? What we do with negative angles is we add 360 degrees until we enter the 0 to 360 interval. So we do that as many times. So after adding 360, take my calculator, I add 360 to negative 180, I get positive 180. Now positive 180 is within the 0 to 360 interval, which means I am safe. Okay, then I write the function value in the right order. Obviously this is positive 180 plus theta. Now you can reduce this thing. 180 plus is in which quadrant? Third quadrant. How is sine in that quadrant? It is negative. Then you write a negative sine of the acute angle. Okay, so what you are doing all the time with negative angles is you are adding 360 as many times as you can until you enter into the 0 to 360 interval. That is the objective. That is why we basically add 360, right? Because we want to go back to that unit circle, which is from 0 to 360. That is familiar ground. So we add 360, for instance, to minus 540 degrees, however many times, until we enter into the 0 and 360 interval. So if you add 360 the first time to minus 540, okay, you're not there in the 0 to 360 interval. You add 360 again, you are there, you get 180. So that means you can now write the function value within the 0 to 360 interval, which is 180 plus theta. Then you can evaluate this. 180 plus is in the third quadrant. How is tan? Tan is positive, so you write positive tan theta. Yeah. So that's what we're doing with negative angles. Here, you add 360. If you add 360 to negative 360, you get 0. So that means you are basically there again. And you can just write that answer. If you add 360, you get cos x. That's the answer. If you had tan of x minus 360, you add 360, you get 0. That means the answer is tan x. If it was sine of x minus 360, you add 360, you are there. The answer is sine x, you know. Here, you would add 360 3 times, you know, because if you add the first time, you don't get into the 0 to 360 interval. You add again 360, you don't get to the 0 and 360 interval. You add 360 again, you get 0, and therefore the answer is cos of theta. Okay, all right. So for angles and negative angles, we add 360 however many times. For angles greater than 360, we subtract 360 until we enter into the 0 to 360 interval. Then we evaluate whatever function or co-function value we have, and then we write our answer. Okay, so that's what we are doing constantly with negative angles and the angles greater than 360. For negative angles, we add 360 until we enter into the 0 and 360 interval. For angles greater than 360, we are subtracting 360 however many times until we enter into the 0 to 360 interval. Then we evaluate whatever function value we have or co-function value, and then we write down the answer. Okay. Guys, those are the two important identities. We know they are true. We know they hold at all times. Okay? Alright? And I hope you guys understand why that is the case. Very, very important. Very, very important. Okay? Now, I want to do the following now, because we have basically done the basic work, the work that has to do with the basics. Okay, very, very important, that work that has to do with the basics. Simi Shabalala, if you want an explanation on compound angles, this is obvious. Sorry, unfortunately, this is unfortunately not the session. This is not the session because I'm doing grade 11 trigonometry, not grade 12. Okay, so I think what we'd have to do though is, if you want, you can go to my YouTube channel. What I did is I actually did a session with the grade 12s on compound and double angles, but this was like introduction stuff, sort of like in the same vein. You can go into my YouTube channel. You can go and look up my latest, I think one of my earliest videos for grade 12s. For compound and double angles. You can check that out. Tomorrow morning at 5:30, you can join me as well, because I do grade 12 sessions in the morning at 5:30. So tomorrow I'll be definitely doing a grade 12 session for grade 12s. Yeah, 5:30 morning, 5:30. I might start a bit earlier because I intend to wake up a bit earlier as well, maybe at 5 to 5:30, at 5 a.m. So hopefully you're an early riser, and then you can kickstart the morning off to a good sweet note together. See me? Hopefully you've heard me there. Okay, then Presh, yeah, what I was doing here is I was just showing, this is not negative, well, it's just for when you have your squares, all right, meaning you have an exponent. Okay, sine squared 180 plus theta. Very important that you put the square around the trig ratio. This square applies to the trig ratio alone. Okay, so you put the square around the trig ratio, you remove it there, you evaluate the function value, you get whatever answer, whether negative or positive, but the minute you apply the square, the answer is bound to be positive. Okay, number 2, the same thing. You put the square, all right, around the entire trig ratio, you evaluate. This is a negative angle, which means you're going to add 360 multiple times until you enter into the 0 and 360 interval. Okay, so you get 0 eventually, so that means the answer is sine theta. You apply the square, the answer is sine squared theta. 3 and 4, tan squared 180 minus theta, same thing. You put the square around the entire trig ratio. You evaluate the trig ratio. 180 minus theta is in the second quadrant, tan is negative, and then you apply the square. That negative becomes positive, so the answer is tan positive, tan squared theta. And then look at this one. There is a coefficient, a half, preceding the square sine squared here, 180 plus theta. So same thing, you put the square outside the trig ratio, you evaluate what's inside, you get a negative sine theta, you apply the square, and then you get a positive sine squared theta. If you see here, this half, it was not affected by the square, because the square only applies to the trig ratio, not the coefficient. So the coefficient is unaffected, and that's very important. Okay, unless of course you had gotten a question where they had put a bracket around the square and it was for everything, then it would have been a totally different story. But just remember, whatever exponent is here, it will only apply to the trig ratio. So you must then first do what? Open brackets, put the exponent that is concerned, and apply that exponent after evaluating the function value. Okay, just something worth noting. Let's say it was to the power 3 here, not to the power 2. Do you understand that had I applied that odd exponent to a negative sign, the negative sign would have stayed negative. It would not have changed to become positive. And these are like basic principles that you've learned even in earlier grades, that an odd exponent, let's say if it was to the power 3, then this negative sign would have stayed negative. Okay, lovely. Like I said, lovely is like, do an example where okay. I mean, it would be, let's say if they had done something like this. This is what I'm saying. Okay. Of course, what you would do here, right? What you would do here, this square is supposed to be eventually applied to everything. But what you are going to do is you're going to work out what's inside first, right? You're going to do that. Work out what's inside first, and then you are going to apply the square. By this, I mean you are going to evaluate this thing. Okay. Okay, this is really just it's really like an example that I've just made up now. So okay, you need to understand that much. Okay, so this is what I mean. So you evaluate what's 180 plus theta. 180 plus theta is in the third quadrant. Cos is negative, so you'd say negative cos theta. Okay, the half is obviously unaffected by the square. The square that applied to the trig ratio, it's unaffected. But then obviously there's this square that was outside that will affect everything inside. So this is half. The square says positive cos squared theta, because this negative becomes positive. Then of course, remember you have this square. So this square then needs to be applied to everything. So that would be 1 over 4 cos to the power 4 theta. Okay, so this is what I mean by, all right, this one will affect everything because there's a square over everything. Okay, but of course this cos squared, when I open the bracket to put it outside, it only affects the trig ratio. Okay, so I think the most important thing here is just to understand that the exponent that is relevant to the trig ratio will only affect the trig ratio. Okay, that's what I mean. Okay, guys, I'm hoping you guys are with me and things are okay. I want to look at something else just very quickly here, because there's things here that we can and we must not take for granted. Maybe just before I do that, okay, before I look at factorization, because there tends to be sometimes factorization situations that involve your trigonometric ratios and expressions. So when there's an expression given to you that's trigonometric in nature, if I say to you factorize, for instance, the following, so you guys must be skilled as well in factorizing trig ratios. So for instance here, sine theta times cos theta plus cos theta, factorize. Do you guys see what's happening here? How many terms do I have in this expression? There are 2 of them. All right, there are 2 terms in this expression because terms are separated by plus and minus sign. Can you factorize this? What type of factorization do you see? And the thing is, this is something we need to take note of. There's highest common factor factorization. There's difference of 2 squares factorization. There's trinomial factorization. And there's grouping factorization. There's common bracket factorization. I guess common bracket and highest common factor kind of come in the same sort of like, you know, group. Okay. And then there's cubic. Now all grade 10s would be familiar with these, but all grade 11s should know these very well because they've just come from grade 10. And being in grade 11, you guys were promoted to the next grade because you are so affluent in all of the mathematical skills covered in the previous grade. So I mean, you guys surely like will be able to be efficient in being able to do these types of factorizations, hands down. Ne? Yeah, no jokes. So if I look at this expression, for instance, can you guys see what type of factorization is to be applied here if I'm applying factorization? Let's just see. Okay, Lovely said highest common factor. Lovely, what is the highest common factor then? If you're saying it's highest common factor factorization, what is the highest common factor? Luba, I see as well, you said HCF. What is the highest common factor? Sin theta, cos theta plus cos theta. The highest common factor is? Yeah, you guys are 100%. So it's cos theta. So you take that out then. And then inside the bracket you are left with, on the left you are left with sin theta. And on the right you are left with plus 1. Yeah. Now you need to know how to factorize. Okay. Let me show you something else. Factorize 1 minus sine squared theta. What type of factorization is here, guys? 1 minus sine squared theta. 1 and sine squared theta are called what? What are they called? 1 and sine squared theta. What do we refer to them as? Okay, so we can clearly see this was highest common factor. Esihle says dots. Yes, very true. Very true. Now, obviously, this is the identity, right? We know 1 minus sine squared theta is equal to cos squared theta. You guys should know this because cos squared theta, if I make cos squared theta the subject of the formula, that means I take sine squared theta over. So my answer is 1 minus sine squared theta. Okay, but I'm not saying to you guys you need to give me the identity. I'm saying you must factorize. Okay, 1 minus sine squared theta. But I was just sort of like bringing that to our attention that indeed 1 minus sine squared theta is equal to cos squared theta. So what if I factorize 1 minus sine squared theta? If it's difference of two squares. So when I'm factorizing difference of two squares, I open two brackets. I know my first bracket and my second bracket will have a plus and a minus. That's one for sure. The square root of 1 is 1 and 1. The square root of sine squared theta is sine theta and sine theta. So therefore this is factorized. Okay, a difference of two squares. Yes, Luba, you are 100% correct there. 100% correct there. Okay. All right. So I'm hoping you guys can see this prevailing need for one to be exceptionally good at seeing this factorization. Look at this one, guys. Sine squared theta plus 2 sine theta plus 1. Okay, so we've established this was a difference of two squares. So difference of two squares needs to also be good. Essentially, it's like on the money there. Essentially, it's like trinomial factorization. So we need to be good there, trinomial as well, guys. Yeah. So if you think about it, once again, since this is trinomial factorization, this is like our square term. Okay, sine is squared. So this is like our square term. This is sine theta. This is like our x term. And then this is like our constant term. You see? So when we factorize, this is like, we would typically write x and x, if you remember, x and x, which is like x squared. But in this case, since we have sine squared theta, we don't use x, we use sine and sine. Because if you multiply the two, we get sine squared theta back. Then we must look for the factors of 1. When we add those factors, they must give us 2. When we multiply those factors, they must give us 1. So yes, indeed, our signs are both positive because plus means same signs. Same as what? Same as the sign of the middle term. Remember, when there's a constant term and it's positive, this means same sign. Same signs were inside the bracket. And they are same according to the sign of the middle term. So then our factors are 1 and 1 because 1 times 1 gives us 1, as well as 1 plus 1 gives us a positive 2. So those are our factors. So this is trinomial. me and you need to be familiar with trinomial factorization. So now your mind needs to really come back, guys. Your algebra. So do you see how key it is? You guys have just come from equations, inequalities, algebra, solving equations, factorizing, completing the square of an expression, those things. So you guys should be at a place now where it's like the algebra is still fresh in your minds, and you can apply the same very concepts that you learned in algebra here in this particular topic, because trigonometry, guys, is not devoid of your algebra. Your algebra is still as much as needed here now more than ever. Okay, and when you make sure that your algebra is fine, you'll be good, man. You'll be good, guys. You'll be so good. You know, just another quick example now here that I'm thinking of: sine squared theta plus 2 cos theta sine theta plus cos squared theta. Fawaz, you are very funny. Fawaz, I think Fawaz, it's in the name for Fawaz. Fawaz and funny, I think they go together. Fawaz is this maths lit? Like when there's theta, is this maths lit? Fawaz, are you doing maths lit? Okay. Sine squared theta plus 2 cos theta sine theta plus cos squared theta. Okay. So once again, all right, this is another trinomial. It's just that it has 2 variables, and the middle term indicates the 2-ness in the variables. Okay, so that's why we would say sine theta here, and then cos theta there, and the addition of both, because cos theta times sine theta will give me 1 sine cos theta, and then the sine theta plus this cos theta will give me another 1 sine theta cos theta, and when I add these together, they'll give me 2 cos theta sine theta. This is no different from having x squared plus xy plus 2xy plus y squared. Okay, where the factorization would be x plus y plus y. This is no different from that. And now this is why I'm saying to you guys, you need to call to remembrance all of your knowledge of factorization when it comes to this particular section. This becomes so important when you start simplifying and doing your identities. Now that's why some people struggle with simplification and sometimes identities, because their factorization is something that's not on point, right? And they fail to make the connection between how in trigonometry you can still have the factorization still flowing and popping like nobody's business. So that's what I want to say to you guys. Do not make the mistake of thinking that you do not need the skills you learned in other grades. Please, please, please. All right. There's grouping, there's cubic factorization, okay? Yeah, the works. Okay, so yeah, this is just a few but limited examples, but I just wanted to give you a glimpse. Okay, so please, as well with the identity, the square identity, you need to be able to express it. Where sine squared theta is a subject, okay, you take the cos squared theta, you transpose it, it becomes 1 minus cos squared theta. Cos squared theta is 1 minus sine squared theta. Okay. Please, please take note of all of that. Take note, and take note. And look here, this is a difference of 2 squares. This is a difference of 2 squares. Okay. Yeah. So I think now we are in the position where I can say to you, well, we can look at some questions that in trigonometry we usually get asked. Okay, and maybe I can look at a few problems that usually get asked in trigonometry. So I'm going to look at these sort of like one by one. All right, and I'm going to first start with the first type of problem that we tend to get very early in trigonometry, which we refer to as the Pythagoras type. Pythagoras type questions are questions that were done in grade 10. So it's not like when you're in grade 11, it's like it's for the first time you're seeing these things. It's not for the first time. So let's look at an example. Let's say they told you are given that tan theta is equal to 5 over 12, and we are told that sine theta is less than 0. And then they say, with the aid of a diagram. With the aid of a what? Of a diagram. Without using a calculator. Without what? Without using a calculator. Determine the value. The value of what? The value of sine of 90 plus theta. Okay? Given tan theta is equal to 5 over 12 and sine theta is less than 0, you can see Esihle is like already ahead of the game because she's like quadrant 3. Okay, so how do we approach these questions? We need to first sketch a diagram. So before we sketch a diagram in very rough form, step number 1, we need to make sure that our trig ratio, okay, if no sketch has been provided, it is our responsibility to sketch a diagram. Some questions you get given the diagram. It's already sketched, the diagram is in a quadrant, so all you need to do is answer the question. Okay? But when the diagram hasn't been sketched, you need to read this and you need to draw from it certain things. So first and foremost, the trig ratio. This trig ratio becomes important. Sometimes it happens that the trig ratio, maybe they give you 12 tan theta is equal to 5. So it becomes your mission to try and get the trig ratio to become isolated. So 12 is multiplied to tan theta. How do you isolate the tan theta? If there's a 12 multiplied to it, you divide both sides by 12. So then tan theta is equal to 5 over 12. Okay. Now, this is very important. Isolating the trig ratio so that you have a numerical ratio on the right hand side. What does this tell you? Tan theta is 5 over 12. Is it a positive number or is it a negative number? 5 over 12 is a positive number. So that tells you what? It tells you that tan is positive. So from that, we must ask ourselves, in which quadrant is tan positive? In which quad is tan positive? So let's first ask that. Where is tan positive? It's positive in the first and the third quadrant. Then 2. Sine theta is less than 0. Question is, what does this mean? Sine theta is less than 0. It means sine is negative. Guys, anything that is less than 0, it means that particular thing, which thing? This thing. What is this thing? It's sine. Sine is negative. Question is, where is sine negative? So we go to our Cartesian plane. Sine is negative in the 4th and in the 3rd quadrant. So this was 1, 2, 3. Then we ask ourselves, where are our ticks? Where do we have the most ticks? According to, we asked ourselves first, where is tan positive? We ticked where tan is positive. Then we asked, where is sine less than 0? Meaning, where is sine negative? We ticked where is sine negative. Then where are we having the most ticks? The most ticks fall in the 4th quadrant. So there we draw, thank you so much, Esil. There we draw our terminal arm. Okay? And if you remember correctly, yesterday, I looked at what I told you guys was the unit circle. And I said that this is like a unit circle from 0 all the way to 360. And this here, the terminal arm, is like the radius of the circle. That's why we say this is the hypotenuse. When we complete the right angle triangle in our particular quadrant, we are able to have the radius the x value, which is the base of the triangle, and then its perpendicular height as well. And that's why we are able to then utilize Pythagoras and other things of that nature, because we have a right angled triangle inside our unit circle. So in the same vein, we are in the third quadrant. So what we do is we complete the right angled triangle, and then bam, there we have it. We go back to tan theta is equal to 5/12. This here also gives us direction. This is like y over x, opposite over hypotenuse. The opposite side over the hypotenuse. I mean, opposite side over adjacent side. Sorry, not opposite over hypotenuse. Opposite over adjacent. So the y, where is y? It's here, guys. But the thing is, we know that y in this quadrant is negative. What about the x? It's 12. We know that the x in this side of the quadrant is negative, which explains why 5/12 is positive, because a negative divided by another negative gives us a positive. Okay? So that explains the positive 5/12 we have there, because it clearly means that there was a negative 5 and a negative 12. Okay? Now what do? We need to find our value of r, the hypotenuse. So what do? We use Pythagoras. Remember that this is our standard angle. This is our standard angle from here to there, this quadrant. But remember, guys, that theta is the reference angle. It is the acute angle located within the triangle itself. So then we're going to use Pythagoras to find r. And then r is squared is equal to x squared is negative 12 squared. Y is negative 5 squared. We get 144 plus 25, which gives us 169. Thank you guys for the answers in the comment section. I love you so much. Man, I've never loved strangers so much. Really and truly now. Okay, so r is equal to, we write the plus minus. The minute you take the square root on both sides, guys, you put plus minus. Why? Because the answer could be a positive answer, it could be a negative answer. So for an equation, we put plus minus. Then we know that, and I said yesterday, that r is always positive. R will never be negative. It's only x and y that change according to the quadrant you are in, but r forever positive. Forever when am I darling? Always positive, you know. And I mean, who doesn't love positive people? Okay, so r is 13, x is negative 12, and y is negative 5. The sketch has been provided. The values of the respective sides are sorted. Now they said, without using a calculator, determine the value of sine 90 plus theta. Oh wow. Sine of 90 plus theta is, let's evaluate this, guys. We now know how to reduce. This is what kind of function value? Is it a function value or is it a co-function value? Because remember, if it is a function value, then I don't have to worry about sine changing to cos. But if it is a co-function value, I need to worry about sine changing to cos. So it's a co-function. Thank you so much, Presh, Sbani, Esihle, and all the others who have answered internally within their hearts. So 90 plus is in which quadrant? Second quadrant. How is sine? Sine is positive, but then we write the co-function cos theta. Then we can now go to our diagram. And then what is cos theta? It is x over r. In other words, negative 12 over 13. Done. We've just evaluated sine of 90 plus theta without using a calculator. Guys, wasn't that just delicious? Like, I mean, guys, did you feel the deliciousness of that meal? Ay. That meal was too delicious, guys. Let's say they asked us to evaluate, let's say they had asked us to evaluate 2 cos squared theta. Okay, so in the same vein, what would we do? We already have this is already a trig ratio. All we know now we need to do is just make sure that this is 2 cos theta squared, right? Remember, our square only affects the cos. Very important. The 2 is unaffected. So what's cos according to our definition here? Cos is adjacent over hypotenuse. In other words, cos is negative 12 over 13. Don't forget the squared. We apply the square. Okay, we apply the square and we get our answer. Okay, so 2 times 144, 2 times 144 over 169 gives us 288 over 169. Okay. Yeah, guys. So all in all, man, yeah, man. These are the things. Really and truly, we just need to know how to do Pythagoras type. Very important type. We need to know. Very, very important. And like I said, this one is where you had. No. Remember, Pigela. This thing of without using a calculator is not so much about not using a calculator in a step. This thing of using a calculator is about not using a calculator from the get-go. Okay. Yeah. Because tan theta is equal to 5 over 12. I mean, you could get theta using the calculator here. You could get what theta is equal to using the calculator from the onset. Okay. But the minute you have the diagram, okay, and you can actually write out all your steps, then basically what that means is that without using a calculator, it's simply saying you must show your steps. You must show the sketching of the diagram. You must show Pythagoras. You must show the answer, getting the answer of R. But I mean, being able to utilize the calculator at a certain step of your steps is not in and of itself what they are meaning by saying without using a calculator. Okay. Yeah. Okay. Kylie said it very well. Very well there. Just you can read that comment. But I have explained that to the learners in the past, and I think we just need to understand it for what it means, so that we do not find ourselves in a sticky situation and then we just complicate our lives unnecessarily. But I'm glad you get it. I'm glad you do. Okay. Another type of Pythagoras type is this one. Sine 18 degrees is equal to A. Use a sketch to determine each of the following. This is another Pythagoras type. Sine 18 degrees is equal to A. Okay. Use a sketch to determine each of the following. And each of the following that I am talking about is sine of 162 degrees, 2 sine of negative 162 degrees, 3 sine of 72 degrees, 4 tan squared of 702 degrees. Okay, so let's look at this again. Sine 18 degrees is equal to A. Kylie, you need to hang on. You need to hang on, brother. I'm coming to those things, but you need to hang on. All right. Yeah. Sine of 18 degrees is equal to A. Use a sketch to determine each of the following. Sine of 162 degrees. So first and foremost, we look at this. Sine 18 degrees is equal to A. That's good. I'm glad you can laugh at that, Kylie, rather than get angry and mad and decide to let's just I don't know. Sine of 18 degrees is equal to A. So we step number 1 is there. we take sine of 18 degrees, we say equal to A, and we say A over 1. Very important, we say A over 1. Now, the trig ratio, the trig definition of sine, according to, in terms of yx and r, it is actually equal to opposite over hypotenuse. In other words, it's actually y over r. Okay, so you have two options here. You can draw a freestanding right angle triangle if you want. Just a freestanding right angle triangle. Or you can just go to the first quadrant of your Cartesian plane, because that's where all trig ratios are positive. As you can see, this is sine 18 degrees, which is equal to A. All right, so we just sort of like, we can either draw a freestanding right angle triangle, okay, and the 18 degrees becomes that angle. Does that make sense? Then since it's A over 1 and it's y over r for the Cartesian plane, y over r would mean A as your opposite side, which is y, and your r will be equal to 1. Okay, so if it's your freestanding triangle, you have 18 degrees, you have A and 1. Okay, then we can use Pythagoras to find the missing variable, which is x, or in this case, it's your adjacent side. So we say r squared is equal to x squared plus y squared using Pythagoras. Then x squared, that's what we are looking for. R squared, that's 1 squared. The y is our a squared. Okay, then we need to make x squared the subject of the formula. So that means we transpose a squared, so we're going to have 1 minus a squared, which is equal to x squared. Do you see, once we took the a squared over, it becomes minus a squared. X squared is isolated. Then therefore we can say x squared is equal to 1 minus a squared. We take the square root, we put plus minus, so x is equal to the square root of 1 minus a squared. But remember, if it's a freestanding, then 1 minus a squared is fine, the positive value. And obviously, if it's in the first quadrant, then x is fine as positive, because remember, in the first quadrant, x is a positive value, 1 minus a squared, the square root of 1 minus a squared. Okay, right. Now we have a diagram, and it's nearly complete. It's just that we have all of the sides of this right angle triangle. 1 is the hypotenuse, a is the opposite side, and the square root of 1 minus a squared is the adjacent side. This is 19, this is 18. What is this angle, guys? Can someone tell me what this top angle is? Because it is very nice when I have all the angles and all the sides. Okay, and actually that is the same as well for this one. You have 90 there, you know, you have theta there. This would be 90 minus theta here, right? It's always good to fill in all the angles and all the sides so that you have a complete right angle triangle that has all the angles and all the sides. Okay, so guys, if that is 90 and that is 18, what is this angle here? This is 90, remember? This is 18 degrees. What is this angle? How would I find this angle that's missing here? Killer, oh, thank you. Pigela, thank you, and lovely. Okay, you guys are lovely, all of you. 72 degrees, guys. Okay, so this here, as a matter of rule, please make sure that when you are sketching your diagram, you fill in all angles and sides. Please, guys, please, you'll see how valuable that is. Once you fill in all angles and all sides, you're gonna have a good time, I promise you, answering the questions. Now let's go now. Tomorrow morning at 5:30, Angel, you can join me tomorrow morning at 5. That's when I'll be doing matrics, doing grade 11 at the moment. So yeah, But remember, concept-wise, you guys are still pretty much doing pretty much the same thing. It's just that you have the interplay of compound and double angles. That's all. Otherwise, you are still starting off things sort of in the similar way. Sine 162. This is an angle that's greater. All right. That's basically not acute. So what is our goal? We need to reduce it. Okay. Yeah. 5 a.m. 5 a.m. in the morning. So let's reduce sine 162 degrees. Sine 162 degrees. Okay. Now we have function values 180 minus. Okay. So 180 minus what will give us 162? Because what we want is the angle that is acute. Remember here we said theta is an acute angle. And I don't know, but I feel like some people get this completely twisted. There are people that will write sine 180 minus 162, for instance. No, guys, you can't do that. Okay? You can, though, go to your calculator and say 180 minus 162. You want to obviously see if you won't get either the angle 18 or 72, because to use this triangle, you need to get 18 degrees or 72 degrees in the mix. So what you do, you're going to say 180 minus 62 and check. Oh, it is 18. So that means 180 minus 18 degrees is an appropriate reduction, is an appropriate acute angle to subtract from 180. 18 degrees is an appropriate acute angle to subtract from 180. Then you evaluate this. You apply the reduction formula. 180 minus is in the second quadrant. How is sine? Sine is positive, guys. So you say sine of 18 degrees. But then remember, what is sine 18 according to the diagram? Opposite over hypotenuse. That's equal to A. Okay. There it is. Done. Sine 162 is done. Okay. So all angles that are not acute, we need to reduce them using our function values. All right. And we need to reduce them in such a way that in the mix of the acute angles we have, we must at least have 18 or 72 degrees in order to be able to use the diagram. Let's look at the next one. Number 2, sine of negative 162. Sine of negative 162. Do you guys remember what kind of angle is this? It is a negative angle. So what do we do to negative angles? Anyone tell me in the comment section, what do we do to negative angles? Because if it's a negative angle, angles less than 0, we need to do something to them before we can actually apply our function value. Still remember what we do? Yes, man, we add 360. Look at the sine of negative 160. We add 360. What do we get? 198. So that means we are going to say sine of 198 degrees. Now we can work with this. We can reduce this. The question is, how do we reduce it? This is going to be an angle more than 180. 180 plus, but 180 plus what gives us 198? So we can check 198 minus 180. What does it give us? Does it give us 18 or 72? Oh yeah, look at that, it's 18. So that means 180 plus is the function value plus what? Plus 18 degrees, the acute angle that is in the diagram. You see, it's working, this thing, the acute angle that is in the diagram. That means we are in the right direction. The acute angle that is in the diagram. So 180 plus 18, we reduce this thing. 180 plus is in which quadrant? Third quadrant. How is sine? Sine is negative. So it's negative sine 18 degrees. We go to the diagram. What is sine? It is opposite over hypotenuse, so it's a over 1. But you know a over 1 is actually a, but then there's a negative sign. That means our answer is a negative a. Done. Done, guys. Done. Do you see what we did here? Add 360. Choose appropriate function value. Choose appropriate function value. Reduce. Reduce. Choose appropriate function value with acute angle. And this acute angle must feature in my diagram. That is the point, guys. And then we reduce. We apply reduction. And then we use the diagram. And then voila. And then happiness and joy forever. Okay. Let's look at the next one. Oh, okay, this one is quite easy. They're saying sine of 72 degrees. Sine of 72 degrees. Now guys, seeing as though we have 72 degrees in our diagram, remember I said fill in all the angles in the diagram. So sine of 72. So this is our angle of reference, right? So if we're looking at this angle, what is sine according to our definition? It's opposite over hypotenuse. So that means the opposite side to the 72 degrees is the square root of 1 minus a squared. What is the hypotenuse side? It is 1. So therefore our answer, guys, is the square root of 1 minus a squared over 1. But we know that is the square root of 1 minus a squared. Okay, I hope you guys can see what I'm saying. Because we filled in all the angles, even the missing one, 72 degrees, they asked us to evaluate sine 72 degrees. If we look at the 72 degrees, for the definition of sine, what is the opposite side of this angle? The opposite side of this angle is this side, okay? It is this one, meaning the square root of 1 minus a squared. What is the hypotenuse? It is still our value 1. Because opposite the 90 degrees, we always have the hypotenuse. So that's why the answer is the square root of 1 minus a squared. Okay, are you feeling me there, guys? Are you with me? Are we feeling why the answer there is the square root of 1 minus a squared? Any questions there? I hope you guys are getting that one too. Okay, and then the very last one, the tan squared of 702. Amukelani Obiana is like saying no, why? Okay, I need to, then you need to tell me what don't you understand. Okay, because I said that we fill in all the angles inside the right angle triangle. We initially had 18 degrees. We had that 90 obviously, which is standard always there. Then to find this angle, I said you need to use the sum of angles in a triangle. If that's 90, if that's 18, what's missing? It's 72 degrees. 180 minus 18 minus 90 gives us 172 degrees. So this is 72 degrees. Now they're asking us for sine 72 degrees. That's what they're asking us. Sine of 72 degrees. Where is 72 degrees? It's there. What is the definition of sine? It's opposite over hypotenuse. So my question is, if you look at 72 degrees, what is the opposite side of 72 degrees? It is the square root of 1 minus a squared, because opposite 72 degrees is the square root of 1 minus a squared. This is the opposite side. Where is the hypotenuse? It's 1. Okay, so that's why we say the answer is the square root of 1 minus a squared. Okay, or someone else could do it this way. Some people would reduce sine 72 degrees to its cofunction using the cofunction value. Sine 90 minus 18 degrees. Those who insist on working with 18 degrees, sine 90 minus 18 degrees. See, now we are using the co-ratio. The angle is already acute, but we can use the complementary. Look at 72 and 18. These are complementary angles. What are complementary angles? Angles that add up to 90 degrees. So in other words, we can use the complementary co-ratio. We call it the complementary co-ratio. So 90 minus 18, if we reduce 90 minus 18, the answer will be 90 minus is in the first quadrant. It is, but honestly, that difference of two squares, we are not going to factorize. Remember, the whole point of factorizing would be to simplify something. So this particular answer, as it is, the square root of 1 minus a squared, we leave it as it is. Okay, this is as simplified as it can get. opening two brackets and factorizing is not going to simplify this any further. So two terms, that's fine. We just leave it like that, okay? So 90 minus 18 is in the first quadrant. How is sine? Sine is positive. Then it would be the co-function cos 18. So maybe get cos 18 would be more appropriate for people to then evaluate, because cos 18, if you think about it, cos of 18, x over r, x, which is square root of 1 minus a squared over r. It's still the same answer, the square root of 1 minus a squared. So those are two paths. This is the second path, leads to the same answer. This was the first path. It also leads to the same answer, and both of these would be acceptable. Whether you chose to go down this path or to go down this path, it still basically is mathematically correct. The approach is fine and the answer is fine. And guys, some people, just something to note, sine 72 degrees is equal to cos of 18 degrees. Okay, and Nontle, I'm guessing you're probably coming in now. Why are we saying sine changes to cos? It's because 90 minus 90 plus 270 minus and 270 plus, these are all called co-ratios. Okay, so co-ratios, whenever we use these function values, sine will change to cos, and if it's cos, cos will change to sine. For 90 minus, 90 plus, 270 minus, and 270 plus, this always happens. There's always that interchange between the two ratios whenever we are reducing a particular function value that has those co-ratios. But with 180 plus, 180 minus, and 360 minus, the change of sine to cos does not happen. The ratio stays, the trig ratio stays the same. It's only the sine, depending on which quadrant it is in, that changes. Okay, so 90 minus, 90 plus, 270 minus, and 270 plus always change, whereas 180 plus, 180 minus, and 360 minus, they do not lead to a change in trig ratio. Okay, so that's something for you to know if you didn't know it, for future benefit and purpose. Okay, all right. I'm going to be ending at 10 o'clock, guys. At 10 I'll definitely be ending, because that's when I have to put my little ones to bed. So let's just do this one without using a calculator. The one for 702. Okay, so I'm guessing you weren't here as well when I did angles greater than 360. Okay, so the one for 702, okay, tan squared 702 degrees. The point you need to get here is that all angles that are greater than 360. Okay, I explained this earlier on. Just so that I can see if I can't get the note that I had basically written down. I explained this earlier on. Okay, all angles that are greater than 360, we need to actually, when angles are greater than 360, we subtract 360 until the angle is within the 0 to 360 interval, right? So for instance, you see 450, we subtract 360. We just use our calculator, we subtract 360 until we get into the 0 to 360 interval. So when you subtract 360 the first time with 450, we get 90, and that is within the 0 to 360 interval. Once we are there, we write down that function value or co-function value, and then we reduce it. Okay, 90 plus is in the second quadrant. How is cos in the second quadrant? It's negative, but since we are dealing with the co-ratio, cos changes to sine, so our answer is negative sine theta. Okay, look at sine 810 minus theta. we need to first subtract 360. Why? Because we have an angle that is greater than 360. So we subtract 360 multiple times until we enter into the 0 to 360 interval. So when we subtract 360 the first time, we don't get there. We subtract 360 the second time, we don't get there. We subtract 360 again. Sorry, actually, we subtract 360 the first time, we don't get there. We subtract 360 again, then we get there. We get 90. Okay, so sine of 90 minus theta. All right, we evaluate, and obviously 90 minus is our co-function value. So that means 90 minus is positive in the first quadrant, but the trig ratio changes from sine to cos. Okay, so that's basically what happens with angles greater than 360. We subtract 360 until we enter into the 0 to 360 zone. So what I did here with tan is I first said tan 702, the square on the outside. What do we then do after that? We subtract 360 from what? From 702. So you take your calculator, you say 702 minus 360 the first time round, we get 342. Okay, oh, had I done that? No, I hadn't done that. Had I done 702? I hadn't done 702. So let me do 702. I thought I did do 702, but I guess I didn't. Let me quickly do 702 for us. Okay, let's do 702. Tan squared 702 degrees. So very quickly, we first take out the squared so that we deal with tan 702. Now this is an angle that is greater than 360. So what do? We subtract 360. Okay, so when we subtract 360 the first time, we get 342 degrees. This 342 is within the interval 342. 0 to 360. So that means we get tan 342 degrees. We now get an angle that is between 0 to 360, because the whole point, guys, of subtracting 360 is so that we can get to the interval 0 to 360. We want to be within the interval 0 to 360 so that we can evaluate a function value that we know. We can reduce this angle using a function value that we know. All right, because our function values are 180 minus, 180 plus, and 360 minus. Okay, so now that we have 342, the question is, what function value can work here? So I basically just check very quickly what's 360 minus 342, because I could use the function value 360 minus. If you can see here, 360 minus 342 is 18. So that means I'm going to reduce 342 to what? 360 minus 18 degrees. Does that make sense, guys? 360 minus 18 degrees. That's how I'm going to reduce 342 to its acute angle. Then 360 minus is in the fourth quadrant. How is tan? Tan is negative. So it's negative tan 18 degrees, that is squared. But then when you apply the square, what happens? It becomes tan squared 18. Okay. Okay. But then you go, oh, sorry. Yeah. Yeah. So I think just before I apply the square, let's say the negative was still there. Then I can go and evaluate using my diagram what is tan. Okay, remember I had a diagram that I had drawn. Okay, I had a diagram that I had drawn, and it was an important diagram because it had my ratios in terms of A. So if I go there, tan, what's tan in terms of the diagram? It's A over square root of 1 minus A squared. Very important. So this is negative a over square root of 1 minus a squared. Okay, very, very important. I substitute that, but then remember, I have to square all of that. Okay, so when I apply the square, I apply the square to the negative sign, it becomes positive. I apply the square to the a, that becomes a squared. I apply the square to the square root, that becomes 1 minus a squared. And that is my answer. Okay, that is my answer. Okay, so I kind of like held back a little bit from applying the square immediately. Evaluate what the trig ratio is with the negative sign, negative tan 18. Use my diagram to state the ratio, trig ratio tan 18 in terms of a. All right, so I used this particular sketch that I had drawn because tan 18 is opposite over adjacent, meaning it's a over square root of 1 minus a squared. But it's negative because remember it was negative. Now I can apply the square. When I apply the square, I apply it to the sign, I apply it to the letter on the top, and I apply it to the square root in the denominator. That gives me a squared over 1 minus a squared. And guys, we cannot simplify this any further. Remember, we cannot cancel a squared and a squared because we do not cancel across an addition or subtraction sign. You leave your answer like this, please, 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 because there's people that tend to think that this a and this a will cancel. You can't cancel those two. This is one term at the top, this is two terms at the bottom. You can't divide. Okay, guys, this is let me show you the absurdity of doing that. Just for a moment, let me show you the absurdity of doing that. If you have 5 plus 1 over 5, okay, let's think about it. What's 5 plus 1? It's 6 over what? Over 5. If you put this in the calculator, you get a answer, right? A very important answer. I think it's 1,2. Okay, now imagine if I did this. My question to you, the person who's cancelling, what's left behind? What is the answer? Is it the same as 1,2? So do you see the absurdity of cancelling across an addition or a subtraction sign? We don't do that. We don't cancel across an addition or subtraction sign. Please, 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 we do not do that. Different story when it's something like this. The relationship between 5 and x is multiply. We can cancel across a multiplication sign. We cannot cancel across an addition or a subtraction sign. Please, guys, please, please, please. Otherwise, that thing is going to lead to our demise. In actual fact, when you cancel, you're left with 1 and 1. So basically, this is 1x at the top divided by 1, but it's actually equal to x. Okay, so that's the absurdity of people that go ahead and cancel across an addition or a subtraction sign. They basically, that just basically means there's a lack of understanding in the basic concepts of algebra, because those things are the things that basically lead to us losing unnecessary marks. Or in actual fact, yeah, Isihle, you are funny. You are funny, even if I must say so myself. Okay, I wanted to then go on to some simplification questions, and then I'll move to an identity, then I'll move to a general solution question, and that will be it. Okay, let's look at this simplification question here. Okay, and please roll with me here. Roll with me. Roll with me. Okay, roll with me. And Dokoto, I will not be able to help you with some geometry, definitely not now and not today, because I am not there. And yeah, currently it's all things trig with grade 11 at the moment, and it will kind of be like that until I think next term. That will be Dogoto, a topic for next term, because next term, in actual fact, probably even during the holiday, you'll see me doing geometry, because that will mean term 1 work will be done, and I'll be sliding into term 2 work, the beginnings of which actually, and then geometry will be a focus for all grades, don't worry. But for now, sorry. Okay, so here we're told to simplify without using the calculator. Okay, in other words, as it says, we need to show all calculations. All angles that are greater, all angles here need to be reduced to acute angles. That's the important thing. So there at the top, what are we going to do? We're going to use our co-function value. Which one? 360 minus, because that one ensures that we have no co-functions where we are going to be changing trig ratios. Okay, so 360 minus 30. What's 360 minus 30? It is 330. This is an acute angle, so that's fine. 100. I know it's 100% fine. This one, sine of 180 minus 20. Okay, 180 minus 20. That's fine. Tan 180 minus 30. Do you see, guys, that in my head I'm just thinking of function values? Function values, 180 minus 180 plus 360 minus. You know, I see 330, I'm thinking of 360. I see of 160, I'm thinking of 180 minus or 180 plus. More specifically, 180 minus. This is acute, this is acute. I'm safe, man. 150, I'm thinking of 180 minus. 180 minus 30. Tan 315. 315, I'm thinking of 360 minus. Minus what? 45 degrees. Okay. Yeah, guys. 45 degrees. And I'm sure you guys can see something. Then cos 110. I'm thinking of cos 180. 180 minus 70. Okay. Yeah. Right. And so what I can see here is that this is a special angle. This is not special. This is a special angle. That is a special angle. That is not special. But there's something very interestingly unique between these two. Okay. And you're going to see after the reduction. So let's go now. 360 minus 30 degrees is in the fourth quadrant. How is cos? Cos is positive. Okay. Then 180 minus 20. Okay. Is in the 180 minus is in which quadrant? Kaloku Sbani, I told you most with special angles. I said when I was doing the things in the beginning that 30 degrees, 45, 60. They are all special, these guys. 30, 45, 60, all special. Okay. Remember in grade 10, you even had special triangles for all the ratios. But now I said earlier on to the people as I was explaining special angles that for 30, 45, and 60, all you do now is just use your calculator and just write those special angle ratios as you see them in the calculator. Yeah, because they have the special triangles. In grade 11, we just need to reduce first and foremost. Please, guys, reduction to an acute angle is very key. Okay. So 180 minus is in which quadrant? It is in the second quadrant. How is sine? Sine is positive. So it's sine 20. And I tend to love using brackets here. I know there's a dot and it means multiplication, but I use brackets deliberately, even though there's the dots, just so that I know brackets mean multiply for me. Tan 180 minus theta, 180 minus in the second quadrant. How is tan? Tan is also negative. Okay, yeah, this is also so that I can be able to know that the relationship at the top is multiplication. That's very important for me. So I insist on putting brackets so that I can sort of like have that relationship very well defined. Okay, then here at the bottom, 360 minus which quadrant? It's the fourth. How is tan in that quadrant? In the fourth quadrant, tan is it's negative most. And then last but not least, 180 minus 70. 180 minus, this is also acute. 180 minus is in the second quadrant. How is cos? It's negative as well. Guys, the marks that you get from right evaluations with the right signs, like this is like literally, maybe there's one mark there's like 1, 2, 3, 4, 5. right evaluation, right substitution. Please, guys, don't mess up here. The signs as well. I don't know why people butcher the signs. The signs, it always goes south. Icon. Now let me teach you something very quickly. There's something here that we call a complementary co-ratio. What does the word complementary mean? Does anyone know what complementary means? My geometry people. Prof, in fact, you all should be geometry people. The word complementary means what? Exactly 90 degrees. Yeah, well, sum of 90 degrees. Okay, two angles add up to 90 degrees. Exactly. Co-ratio. All right. If you remember this co-ratio thing, it's when sine changes to cos, cos changes to sine. Okay. Now, sometimes you look at two ratios and you can see that they are complementary. Two, they are co-ratios. I want you guys to pay special attention to these two. You see this one? You see this one? Don't mind the sign. These two things, they are the same. They are the same. Why? Because they are complementary co-ratios. Yes. 20 and 70 are complementary angles. Doesn't 20 plus 70 equal to 90? Yes. Sine and cos are co-ratios. So this means that these two are the same, these ones. So this divided by that gives us 1, but negative 1. In other words, I can cancel these two. But what's nice is for the person who is doing the maths, who is busy, it's very nice when you can, in the next step, write these two as the same thing, right? Because, for instance, if you were to reduce cos 70, let's just look at, I'm going to show you how I'm saying they are the same. If you reduce cos 70 and you use the co-function, this becomes cos of 90 minus 20, right? Do you agree? If I use the co-ratio, co-function. Then, what is 90 minus 20? 90 minus 20 is in the first quadrant. How is cos? Cos is positive. But then I write sine of 20 degrees. Do you see what I just did? This cos 70 is now equal to sine 20. Okay? Obviously, because there was a negative sign, it's negative sine 20. Do you see that? So these two are the same, which means you can cancel them, right? Because you are not canceling across an addition or a subtraction. So at the top, it's all multiplication. At the bottom, it's all multiplication. And this line means divide. So cancellation is possible. There's no cancellation across an addition or a subtraction sign. But anyways, what I'm going to do is I'm going to first cos 30, express these as special ratios. Cos 30, let's go, because that's where I get my next few marks. Cos 30, square root of 3 over 2 times sine 20, that's fine, negative, what's sine? Negative tan 30, let's go, tan of 30 degrees, use your calculator, negative 3 over negative square root, okay, do you see, over tan 45, do the same thing, tan 45, 1. My goodness. You see, these people are not listening to me. How many times will I say this thing of not using? How many times, guys? How many times do you want me to say this thing, this explanation of without? What did I say, guys? Without using a calculator simply means they don't want me to put all of this in the calculator and say equal and then write the answer and say I'm done. When they say without using a calculator, they are saying you must show your steps. This is what I'm doing. I've shown my steps. Okay? And then now in grade 11, in grade 10, you guys were supposed to sketch the two triangles, 1 root 2, 45 45. This was grade 10. Then you use these special angle triangles to evaluate 45 degrees, and you use this special angle triangle, this one, 60 and 30 degrees, to evaluate 60 and 30. But now when you are in grade 11, you are free to take your calculator and substitute the ratios from the calculator for all the special angles, 45 and 30 and 60. You can just use your calculator for the 45, 30 and 60, guys. Okay. Yes, I forgot the negative. That was just my mistake, my fault. All right. Yeah. Okay. Then what I wanted to do here is to change this cos 70 to the what? To the co-ratio, because I said these complementary co-ratios, they are the same. So sine of 20 in the numerator, all right, in cos 70 is negative sine of 20. Okay, now I will cancel and I'll be left with 1 and negative 1. Okay, now I will multiply what's at the top. Root 3 times root 3 gives me negative 3 over 2 times 3, which is 6, over negative 1 times negative 1 gives me negative 1. Then obviously this is negative 1 over 2 divided by negative 1, which basically gives me a positive half. Guys, do you see this? Okay. Remember, if you wanted to, okay, you should, Ronnie, it gives you, yeah. So, yeah, that's it. That's the answer. Okay. Root 3 times negative root 3 gives you negative 3. Okay, then negative 1 times negative 1, oh, it gives us positive 1. Very true, very true, so true. Okay, very, very true. Yeah, I didn't consider this sign. Very, very true. My apologies, guys, my apologies. Prone to error, but you know, when you are around, you guys, you help. Yeah, no, you guys are 100% spot on. My mistake, my fault, my error. But you guys are phenomenal. So you see, as the learners, you will definitely be doing things 100% correct, because if you can spot this man's error in the question, you guys will be killing it. Yes. Well, Chocolava, that's fine. That's fine. I need to be extra careful as the teacher, but you know what, when you have vigilant learners watching someone do some work on the board, then they will be able to say, no, that is not right, it's you know, you should be doing that. Okay. Nati, all I did for tan 30, I didn't waste no time. I just said tan 30, I put it in the calculator. Okay, I put it in the calculator. Do you know, guys, why instead of using those triangles, I can now do this and put it in the calculator? In, what is it? Didn't you guys, because obviously tan 60 will be tan 30, sorry, will be equal to 1 over root 3. According to your special triangles, it will be 1 over root 3. But you remember, guys, that you guys have learned about in exponents and sets rationalizing the denominator. So what's beautiful is that your calculator does it for you. It rationalizes your denominator for you. It rationalizes your denominator for you. So you can write the rationalized answer as per your calculator. And guys, I am seriously saying that it's fine to utilize your calculator for these special angles in grade 11. Not in grade 10, in grade 11. Don't do it. In grade 10, you can't do this. In grade 11, you can, because you've learned that rationalizing the denominator is a reality. You multiply the denominator by its conjugate. Okay, and in grade 12 as well, you can do it, you see. But in grade 10, you can't, because in grade 10, you guys still learn about the special triangles, drawing the special angle triangles, and then utilizing the ratios of the special angle triangles to basically substitute them in the place of special angles. But in grade 11, we can go straight to where Gufeli Tola corner. We can go straight to where our enemy is to die, so that we can get that answer. Let's see who said, but please repeat there from fractions, my network. Okay, so like I said, we reduced. Okay, cos 30 degrees, I just took my calculator, guys. All I did, I took my cos 30, root 3 over 2. There, I put substitute. Okay, and I put brackets, nice. Sine 20. Sine 20 obviously is not a special angle. I leave it as it is. Negative tan 30. I put it in my calculator, I got root 3 over 3, it's negative. Minus tan 45, tan 45, I put it in my calculator, I got 1, it's negative. And then negative cos 70, I said these two guys are what we refer to as complementary coratios. Take note that sometimes you will have some angles that are not special angles, but they will exhibit the qualities of complementary. What does complementary mean? Addition to 90. That means 20 and 70 are 90 degrees when you add them together. Co-ratio. What does co-ratio mean? It means sine and cos. Cos and sine. So that means these two are actually the same ratio. They are the same ratio. You can either convert this to cos 70 whilst this remains as negative cos 70, or you can change this to sine 20 whilst this remains as sine 20, but this one is negative. And then when you cancel, obviously the sign remains 1 at the top, negative 1 at the bottom, and then you multiply what's left over. Root 3 times 1 times root 3, that's negative, is negative 3, and then 2 times 3 is 6. At the denominator at the bottom, we have negative 1 times negative 1 gives you positive 1. Then negative 3 over 6 divided by 1 gives you a negative half, and the answer is basically a negative half. All right. Yeah. No, I'm happy, Black Paper, that you are saying my life is appreciated. I appreciate people that appreciate my lives. I don't want to lie. I love it. It makes me happy. It makes me rejoice, that thing that people appreciate their lives. Like nobody's business. All right, so let us look at so that was for numerical value simplification. Let's look at maybe another one that does not involve numerical values. Maybe it involves some other. Utula is like, can you explain complementary angles? My guy, complementary angles are angles that when you add them together, they give you 90. Okay. And then I said co-ratios. All right. Co-ratios, sine is the co-ratio of cos, and cos is the co-ratio of sine. So complementary angles are simply angles that add up to 90 degrees. And then co-ratios are like sine and cos, cos and sine. All right. Cos is the co-ratio of sine, and sine is the co-ratio of cos. So therefore, I'm saying between these two angles are not special. That's the first thing. 20 and 70 are not special angles. Sine and cos are actually co-ratios. So they are co-ratios first and foremost, sine and cos. But then 20 and 70, when you add them together, they give you what? 90. So meaning they are complementary. So complementary co-ratios, what did I say? They are the same ratio in actual fact. So that's why, for instance, I did take cos 70 and I basically reduced it using the co-function 90 minus because 70 can be written as 90 minus 20. 90 minus 20 is in the first quadrant. When I reduce it, it becomes obviously it's the negative sign that was there is still there, but cos is actually positive in the first quadrant. But when I write the ratio, it becomes sine 20. So you can see that these two are the same, because they are complementary co-ratios. So that's why I was saying that you can simply do this. You can just simply change this to sine 20, because it's a complementary co-ratio of this one. Or you can change this one to cos 70, all right, whilst this stays as cos 70, and then these two will cancel each other, you see? And then you are left with your special angles. And please, the signs, they are important. The signs here, they are important, because if you butcher the signs like I did in the beginning, then you need to just be careful, right? Okay, allow me to move on, guys, now to this guy. Okay, now this is a simplification question. They asked you to simplify. Okay, simplify. Okay, cos negative x times tan 180 minus x. Then there's a bracket. Brackets mean multiply, but inside the bracket you have sine of negative x plus, and then you have a fraction which has function values, and then you have a bracket. So basically this is a bracket, and then this is multiplication that is outside the bracket. Okay, hopefully that makes sense. So what do we do in these situations? Now people, there is a strategy that I want to suggest. It doesn't matter whether you are doing identities or you are doing the simplification of questions like this. There is a strategy that you need to apply when doing these questions, and this is the strategy. 1, you need to first simplify. Strategy number 1 that you need to apply in problems like this is you need to simplify. And what do I mean by that? There's a family of things that I mean by that. If they are like terms, you can add like terms, and you can also subtract them if they are. 2, if there are fractions that you need to add or subtract or multiply and divide, you must do that. Okay. 3, if there are function values that need to be reduced, in other words, reduction, you must do that. It must be done. All right. So I'm saying like terms, you must add or subtract them. If there are fractions, you can add or subtract, multiply and divide. If there are function values that need to be reduced, please reduce them. Okay. But if all of this is done, then you need to look at strategy number 2. And that is you need to factorize. Now with factorization, there is many types of factorization. There's highest common factor, difference of two squares, trinomial, grouping, etc. If you have exhausted that and it's done, you can always go back and check, is there any further simplification that can be done? If there isn't, you check, is there any other factorization that can be done? If still there's no factorization, then there's the last strategy that you need to apply, and that is you need to check if you can't apply a particular identity, whether that be this identity, the quotient identity, or this identity. Remember, where tan theta is, you can substitute and write sine theta over cos theta. Sometimes where sine theta over cos theta is, you can write tan theta. This one, if you have the square of sine and cos, it's equal to 1. Or alternatively, guys, 1 minus, sine squared theta can also be written as 1 minus cos squared theta, or vice versa, cos squared theta can be written as 1 minus sine squared theta. So these identities, sometimes you can utilize their substitution if there is simplification and factorization strategy have been applied. Identities sometimes will basically loosen up the situation so that you can be able to simplify maybe further. So with this simplification, sometimes multiplying out or distributive law is something I forgot. Okay. These strategies, you see these strategies, guys. Yeah. You jump between these you jump between simplification, factorization, identity. When one doesn't work, you jump to the other. You check if there isn't anything that has to do with this. If there isn't that, you jump to check the other. I'm telling you, bro. I'm telling you. Then it's like the maths, just maths is, and the joy comes in the morning, Yeah, all of that stuff. So like I was saying, that's basically how we go about things when we are doing these things. So let's look at this. So like I said, cos, this is a negative angle, times tan 180 minus x, that's a function value. So that's a negative angle, that's a function value. Here inside the bracket, you can see there's a negative angle plus there's a function value, So it's like here, I can see there's no like terms, for instance. There's no multiplication and division of fractions. Yes, of course, there is this, but I mean, the simplification that needs to happen here is one of what? Of function values, reduction, negative angles, the works. Okay, negative angles and angles greater than 360. That's basically everything tied into function values, co-function values, the works. The whole entire work here. So the only simplification that I can do here is of that, and that's what I need to focus on at the moment. Okay, so I'm on simplification mode and I'm going to apply it. Cos of negative x, this is cos, I add 360 to x. Hey guys. All right, so I'm gonna evaluate these shortly. I just added 360 there because it's a negative angle. All right, puts a totally different dimension to things. Added another 360 there because it's a negative angle. 180 plus x. I'm coming back to you. I'm going to evaluate you. Sine of 360 minus x. You guys are looking good. You look scrumptious. I'm going to scrumptially dish you. Okay, 360 minus, let's evaluate the function values, guys, because we are literally no like terms, addition and subtraction, multiplying and dividing, function values. That's the simplification we need to do. So 360 minus x, 360 minus in the fourth quadrant, how is cos? Cos is positive. My first mark is in the bag. So delicious, guys. I've got my first mark just from evaluating that cos. Yeah, 1 mark is better than 0, guys. Yo. Since there's multiply, tan 180 minus x, I'm going for my second mark. 180 minus x is in the second quadrant. How is tan there? It's negative. There's my second mark. Munati fela. 360 minus x, let's evaluate him as well. 360 minus x, fourth quadrant, sign is a negative. And guys, I'm sure you are seeing I'm putting all of these in small little brackets, guys, small little brackets, so that it does not interfere with my cooking. 180 plus x, you make potatoes, you kind of like a potato salad, you put it in a little cup, put it in a little bowl, you cook, you put it in a little bowl. Yeah, 180 plus x, obviously anything that comes out of here will be positive at the end. But I mean, initially 180 plus x, Third quadrant, cos is what there? It's negative. Okay, but I put the bracket because I'm coming. Sine 360 minus x, fourth quadrant, sine is what? Is negative. Nicely negative. Okay, hi, this looks good. If you ask me, it's looking good. It's looking nice, looking very nice. Outside the bracket, I have multiplication. That's fine. Odd mass tells me about the brackets inside, but outside, for now, we are looking good. Inside, we're going to deal with the inside. We're going to deal with you. We are going to also deal with you. We'll deal with you shortly. So for now, let us just say cos x, negative tan x. I'll deal with them. I also want to deal with the inside here. Okay, so obviously that becomes plus cos squared x over sine x plus negative sine x. So this positive and this negative, obviously this one is applied, but this positive and this negative here, guys, I hope you understand. This positive and this negative gives me a negative here in between. So I have negative sine x minus cos squared x over sine x. Okay, cos squared x over sine x. Inside the bracket, I have a subtraction of fractions, and this is what I want to obviously gonna focus on, because board mass tells me that. So I evaluated the simplification. Why 360 can be blank, sir? What do you mean? Why 360 can be blank? I don't understand what you mean. Tohu 360 can be blank. I don't understand. 360 can be blank. Someone help me understand what Tohu is saying there. Alright. So this cos x, alright, I can write this identity. Okay, do you see this? This tan x I can write as the identity minus sine x over cos x. Okay, I can write it as the identity. Very, very important, the identity. Okay, then inside this bracket I have minus sine x. I'm going to write it as minus sine x over 1 minus cos squared x over sine x. Now there's a little trick that I learned, guys, about when you are adding two fractions. Okay, yes, Andy, you do always, if the angle is negative, add 360. Yes, very, very true. Very, very true. Because we add 360 tohu. Okay, whenever we, or tohu, I don't know what's your name, but whenever we have a negative angle, guys, negative angle, we add 360. Okay, I added 360 here because this angle is negative. I added 360 here because the angle is negative. 360 minus is a fourth quadrant phenomena. 360 minus is a fourth quadrant phenomena. Okay, so therefore when I added 360 there, okay, 360 minus x, obviously this is in the fourth quadrant, cos is positive. 360 minus here, sine is negative. Okay, but remember, guys, what I said about putting a value here that is acute, so that you can always check what the sign is.